in this way, the operator algebra is correct. Yeah, basically you can map gamma up to minus gamma down and gamma down to gamma up. This is a very simple exercise because when you commute this gamma up to gamma down, this pair to gamma up is anti-commute. So that's why you can get this additional sign. But on the other hand, you can easily check that this time reversal operator, it satisfies the algebra T to fourth power to minus 1. Because if you square this operator, because all the operators are real, so you don't worry about this complex conjugate. So when you square this, you just get gamma up, gamma down. But when you further square it, you just compute this algebra. Because this Majorana operator, they are anti-commute, so you end up with minus 1. So that's a very simple calculation. And this is consistent with the proof by mapping the Fermion system into boson model. Okay, now we end up with the conclusion that for a single pair of Majorana zero modes, they must satisfy this very strange time reversal symmetry. It's kind of square root of prime evidence. And we can also work out this representation theory of this kind of time reversal symmetry. So if we combine this left side fermion, gamma up and gamma down into some complex fermion, then we can make a two-dimensional Hilbert space, right? And this fermion operator transform into its dagger because this time reversal symmetry must change fermion parity. And if we work out the representation theory through some tedious calculation, you find that the only difference from the Fermion W is that on this side it's not minus 1. You take a square root, you get a plus minus I. That's why it's T to fourth power to minus 1, not T squared. Okay, so such kind of strange property make us have a cartoon picture that this zero mode is really like ghosts, because when you reverse the type, they change the fermion parity because the vacuum like nothing. Then you reverse time, you can tend to the occupied state in a vacuum. So kind of when you remove your reverse your moving, you find something disappears. So that's the classical story of ghost movie, I think. Okay, so such kind of strange time reversal symmetry actually can be realized in two-dimensional topological superconductor as well as three-dimensional topological superconductor. So the idea is actually very simple. So in 1 plus 1D, you can localize this zero mode on the end of open chain. And in 2 plus 1D, you can actually create some vortex, some defect. And on the defect, you can check a pair of Majorana zero mode, and you can show they actually also carry this same T to fourth power to minus 1 time reversal symmetry. And in 3 plus 1D, you can make a monopole, and in this monopole, you again can have a pair of them. But the 3 plus 1D story is interesting because in a 3 plus 1D topological superconductor, there must be a flux line connected this monopole and antimonopole. And there are some calculations showing that actually the monopole and antimonopole are always in a confinement phase. It's really like a molecular. Then we have a single picture like in 3 plus 1D, the most natural fundamental objects actually will evolve 4 Majorana zero modes. Because a single Majorana zero mode is not allowed, because in 3 plus 1D you can show that point-like particle can only carry boson or fermion statistics. But this Majorana zero mode turns out must carry some anion-like statistics. So in 3 plus 1D, they must be paired up to form actually either boson or fermion states. But on the other hand, due to this kind of confinement in a real world, most likely we will see 4 of them, not 2. And the 4 of them, actually, if you introduce proper dynamics, they can just have this relativistic dispersion, and looks like described by a Majorana field. So let me just give you one simple example. But of course, this example not enough to explain the whole standard model. But actually, I don't know how to consider exactly lattice model regulation or other regulation to reproduce the standard model. But the idea is that if we assume there are some fundamental skill, we can really cut lepton Fock into two pieces, then we can have this very strained T-CT -1 symmetry. And in this model, I just show that in such a lattice model, if we have a long wavelength dispersion, this 4 will just behave like a fermion field on a single point. So in this lattice model, basically, I put some color here. So the blue color just means it's kind of hopping with amplitude 1. And this arrow just means I or minus I. And this green, I think, is also 1. And the dash green is minus 1. So it's just some Hamiltonian with some complicated hopping. And in condensed matter, sometimes we call the pi flux hopping because the hopping along each plaquette get a minus sign. And if we diagonalize this Hamiltonian, you will find that at low energy, around a certain momentum point, it just have this wire fermion dispersion. So it's really like a Majorana field. So the idea is that at lattice scale, we naturally have an AB sublattice structure of this system because this oscillation property of this hopping pattern. So we have AB lattice structure. And in the long wavelengths, this AB lattice, sublattice in a unit cell should be viewed as one point. And this single point will become 4 components. And it could be described by this 4-component real Majorana field. But the point is that at a cutoff scale, you can still see they are separable, and each of them carries some further fractionalized T-cortical -1 symmetry. Okay. So if we take such kind of assumptions, we can further discuss the other more exotic discrete symmetry for Majorana zero modes. For example, I will also show that actually for a pair of Majorana zero modes, they can also carry this so-called P-cortical -1. So this idea is very simple, just as analog to the construction of this time-reversal symmetry. But you just define this operator in a slightly different way. For example, for this, because the parity will not change the spin, right? Parity symmetry will preserve spin, time reversal will flip spin. So we can just define this parity operator like also some pile of 4 circuits, and but with a pair of gamma up prime, not gamma up, gamma down. So it's also P equal to -1. And of course, for a 4-component field, we will evolve 2 pairs. And finally, for this, the action on these 4 modes, just like in such a way. And further, we can show that in terms of some complex mode. So the complex mode is really like a spin up or spin down pattern. So they just transform in a very normal way. But here we have a sign I, which is magic because if we act parity twice, which is just like a 2-pi rotation, and then we will get minus sign for fermion field. And so here we can also make some different bases. For example, we can glue this gamma up and gamma down to form a complex fermion. It's just like this 2 ends of this previous topological conductor I'm talking about. So each end is really like I call it a chiral basis, and under this parity you can map left to right, right to left. So it's also you can naturally integrate these 2 pairs, particle or antiparticle. Okay, so this is some other simple kind of algebraic exercise. And furthermore, you can also do some more exotic. You can think about, you can even map this gamma up to minus gamma down prime. For the time reversal, just map gamma up to gamma down. But for parity, just map gamma up to gamma upper prime. So upper prime just on the kind of right side. So it's like a parity operation. But here you not only map left to right, you also flip spin. So it's really like a child conjugation or particle Hall symmetry. So in this way, you can show actually for each pair, it's also satisfied this C2 4th power equal -1 symmetry. And the action on this complex mode is also in a expected way. So it's a very natural construction of this C.P.T symmetry for the Majorana fermion. And it turns out in this kind of four Majorana zero modes, which form a Majorana fermion, you can have a complete C.P.T superalgebra. So here I'm only considering this one particle symmetry operation, and later I will just generalize everything into quantum field theory. But it turns out the algebra is the same. So here just a very simple algebraic calculation for this single particle. So it's not a quantum field theory yet. But if we talk about the global symmetry, C.P.T symmetry is enough to just look at this single particle picture. So the point is that if we consider some Majorana fermion made by topological zero modes, this fermion parity must be evolved in this definition of C.P.T symmetry, because in this zero mode sector we naturally have degenerate parity even and odd state. And in the fermion parity even state, basically all these C.P.T symmetry they are commute. And this odd state they can become anti-commute. And that's the strange point of this kind of superalgebra. And further, you can check that this superalgebra they commute with the spin rotation symmetry. And then we can show that this algebra can be promoted to a relativistic quantum field theory as well, because in the quantum field theory, C.P.T symmetry must commute with the spin rotation symmetry. Okay, so now let me just show you how to construct this C.P.T transformation for a field theory, not a single particle. But the generalization is kind of very straightforward. We can just think about this real Majorana field, the four components. We can rewrite it into this SO2 real Majorana basis, namely cosine and beta. So each two you see they carry this like a T equal minus 1 counterparallel symmetry. And we can also define this C.P.T operator correspondingly, just by integration over this coordinate number. So here, this quantization process is in a very standard way. You think about this real fermion, they satisfy this canonical quantization relation. And this C.P.T symmetry can be write down in terms of product of each operator on each position. And also, for quantum field theory, I need to introduce some additional global action on the coordinate. So P0 basically kind of map this coordinate x to minus x. And here also I need to impose this complex conjugate that map t to minus t. So in such a setup, you will see that this C.P.T algebra is also well defined for quantum field theory, not just for a single particle level. Okay, so in such kind of setup, we have a new understanding about this C.P.T symmetry definition of Majorana field. But I also want to give you some intuition about why this C.P.T is kind of interesting and reasonable. We can also benchmark this definition of C.P.T symmetry with the standard definition of C.P.T symmetry on derived fields. So we can just choose some particular gamma matrix representation here. So you see all the gamma matrices are real. Right? So gamma 5 is also real here. Okay, so then this charge conjugation basically is up to some phase, just like swipe this two spinor basis, but also kind of flip spin. So this parity just swipe this fermion basis, and this time reversal don't swipe basis, just a flip spin. Okay, so if you compare to complex fermion, actually you see that they're actually pretty similar. Because the complex fermion, we also have this, must go to this complex conjugate. So we have star, but here we just don't have star. But in this sense, these two transformations, they just differ by some minus sign, and all the other action, they are the same. So if classically you can view this kind of Majorana field like just half of this complex field, it's very natural to define the C.P.T symmetry in such a way, and make them satisfy this C.P.T superalgebra. So this kind of definition is very different from the usual definition in a quantum field theory book for the Majorana field. But the only difference, I think, is that I add gamma 5 for the parity symmetry, which actually is allowed because usually in quantum field theory book, people think P and T must commute. So both of them just an action of gamma 0. But from this point of view, it's not reasonable because from a parity symmetry must have different action on the on this spinor basis compared to conjugation symmetry. So we cannot make the same gamma 0 action. We must have add something different. The gamma 5 is something we can use here because it's commutative with the Lorentz symmetry. Okay, so now I try to explain this origin of this neutrino mass and I try to compute this mass mixing matrix based on the previous well-defined C.P.T algebra. So the point of this mass term is that you can check that it's invariant on the P.T symmetry, but not invariant on the charge conjugation symmetry. Basically, you can check that this mass term is take a minus on the charge conjugation. And this kind of symmetry property promotes us kind of try to think about this charge conjugation would be some local symmetry, and then we can introduce a Higgs mechanism to generate this kind of mass term.
Sorry. And let me ask a simple question. The C.P.T you define here is the same as the C.P.T in the Majorana presentation, in the usual
it's different, yeah. I just said it's different because in the usual textbook you can think about the C.P.T symmetry action, the P and T they're the same action on the spinor basis. In such a way, P and T they are commute. But in my representation, I point out the crucial thing is that they must be anti-commute.
So even in the Majorana representation, it's still different.
Yeah. Even in the Majorana, yeah. I'm comparing in this Majorana representation. And in the usual charge conjugation have a trivial action, but here I claim it must have a gamma 5 action. It's not a trivial action. Because although this Majorana field is real, does not mean charge conjugation must have trivial action in the internal basis. You can also make rotations, so just like gamma 5, which can vary with everything. So in such a definition, the charge conjugation, because it's a unitary symmetry, because it's for real fields we don't need a complex conjugate. It naturally can be promoted to a gauge symmetry, and also from the quantum gravity point of view, global symmetry is not reasonable. Any kind of global symmetry must be promoted to local symmetry. So, and also in standard model, we also observe that other symmetry, basically they are local symmetry, not global symmetry. So, if we promote this charge conjugation unitary symmetry into a C2 gauge symmetry, then we can actually understand this mass term, origin of the mass term as a spontaneous symmetry breaking of this C2 gauge symmetry. And we just need to introduce a scalar field that carry C2 charge 1. Then the combination of this scalar field and this mass term, they could be charge conjugation invariant. So the whole action formally can be written down in such a way, but I don't specify the definition of this covariant derivative because for Z2 gauge symmetry, basically it's a topological gauge theory. So we can either introduce some lattice regulation or introduce some topological BF theory to describe this Z2 gauge theory. So I don't want to go to the detail here. But the idea is that we just need such kind of coupling and condense this fundamental scalar field. We can make a mass term for the right-handed stereo Majorana field. And once we introduce the correct pattern, mixing pattern, then we can explain the observe the mixing pattern for the left-handed neutrinos. So that's the basic idea. Okay, and I also have a couple of comments for this potential fundamental Z2 gauge field. First comment is that since right-handed neutrino does not carry electric weak charge, so its coupling to left-handed neutrino is not natural. It's kind of like another fine-tuning because in a classical picture, the coupling must be induced by some interaction. If there's no interaction, it's completely unnatural that the coupling field. And the second point is that this Z2 gauge force provides us a natural way to explain the coupling between this left and right-handed neutrino. And also, it's essentially a topological gauge theory. So the conjecture is that it might have some deeper connection with the origin of gravity. Okay, so now with this kind of conjecture, we can answer the interesting question why there are 3 generations.
I'm sorry, could you elaborate again where the Z2 symmetry is? Is it coming from the gamma phi?
Yeah. Yeah, basically this Z2 symmetry action is like gamma phi on this Majorana field. Yeah, it's a charge conjugation symmetry. So the action on the Majorana field is gamma phi. So you can promote it to a local Z2 symmetry and introduce the Higgs mechanism to generate mass. And now we just have a simple answer for the reason of 3 generation, because the idea is pretty simple, kind of like we have 4 locally separated zero mode. And then at long wavelengths, we must pair up them, because in 3 plus 1D, any point-like particle cannot be a single Majorana zero mode. It must be a pair of them due to the weight and long. Also, or in some other arguments, it must be either fermion or boson. We cannot have really any. So this single Majorana zero mode appears in 1 plus 1D, 2 plus 1D, but in 3 plus 1D, it must appear as the end of some string. So in the long wavelengths, in some sense, we must pair up them. So then it turns out we happen to have 3 different ways to pair up them. And such kind of picture naturally answers why there are 3 generations. And once we understand the reason of 3 generations, we can even do more things. For example, like compute the mass mixing matrix. But before that, I also further try to kind of clarify the basic assumption here. So the basic assumption is that at the cutoff scale, the local Fock space is expanded by a pair of Majorana zero modes. So each pair of Majorana zero modes actually is a 2-dimensional space. It's not 4-dimensional. So in usual quantum field theory, we assume that the fundamental Fock space is always 4-dimensional, right? Because complex fermion carries spin up and spin down. And you can also have a pair or have no fermion vacuum. But such kind of assumption has never been examined by experiment. And we can naturally assume that the fundamental Hilbert space can be further fractionalized. So for example, in the previous kind of lattice model, on each lattice point, you only have a 2-dimensional Hilbert space formed by a pair of Majorana zero modes. So that's a key assumption. Let me just maybe skip this comment because of the limitation of time. So let me just show you that this kind of picture will indeed lead to a natural way to compute the mass mixing matrix. So the cartoon just in this way. So kind of at a certain scale, you need to confine this to Majorana zero mode to make it like a point-like particle. They must be attached by some string, which may be strongly fluctuating at cutoff scale. So in the end, you can have 3 different ways to define this complex fermion basis. And once we specify this complex fermion basis, then this Majorana field is completely the same as the usual wild fields. So in the kind of we can define 3 different kind of wild fermion fields. And each of this local Hilbert space can carry either T quadratic equal to -1 or TP quadratic equal to -1 or even TC quadratic equal to -1. So the algebraic calculation is pretty similar to this T quadratic equal to -1. In field theory, you can also examine that if you make a different local spinor SO2 spinor basis, for example, this time reversal T quadratic equal to -1 spinor basis made by gamma up, gamma down, you can define this SO2 local spinor basis in this way. But for the other 2 generations, you can just make them in different way. For example, for the TC quadratic equal to -1, you can just define gamma up prime, or gamma down prime. And it's easy to see that they transform differently on the C.P.T symmetry, right? And also the final generation, they also transform differently on the C.P.T symmetry. So that's reasonable that to say that we really have 3 generations at low energies. So there's a final detail is that for the last generation, we also need to slightly modify the definition of the Lorentz generator. So it's a detail I will explain maybe in the next slides. So now we can write down some C.P.T. invariant mass term, also Lorentz invariant mass term. So you can check, this is the only kind of mass term you can write down with respect to all the symmetries. And if we assume this fundamental Z2 gauge impression is kind of universally coupled to all these Majorana fermion field made up by Majorana zero modes, we can just tune all these coupling to the same. So here I just choose one diagonal coupling and another kind of off-diagonal coupling. But later I can show you that these strengths of these 2 coupling actually could be chosen as the same. And for the last generation, this Lorentz generator should be, the boost generator should be defined in a slightly twisted way, not the gamma 0 gamma I, but it's gamma 5 gamma I.
And so what's the motivation to tune the off-diagonal couplings to be the same again?
It's a semi-classical argument. Because you can imagine semi-classically they made by the same Majorana zero mode. And this impression actually is Z2 impression between Majorana zero mode. Yeah, so in a quantum field theory, probably needed to impose some kind of symmetry for this mixed matrix. But yeah, that's alternative way. So we also try to formulate it completely in terms of quantum field theory. That's more complicated. So here, this you can think about just a very simple semi-classical argument. Yeah, also there are some detail that we can make some transformation and make this mass term more fit to this standard formalism. Because in the standard formalism, we always assume that these Majorana fields, they transform in the same C.P.T. representation. So we need to do some kind of field redefinition to fit this standard kind of definition of mass matrix.
Sorry, for neutrinos, if they participate the weak interaction, then I would think they don't have to satisfy C and P alone. But do you need?
Yeah. Here the point is that this C and P is different from the standard model C.P.T.
Okay.
Yeah. So because this C and P can be defined just for a single Majorana field, which is equivalent to a wire field. But in standard model, you always map the left-handed wire field to right-handed wire field on the parity. So this definition is different. And under this different definition, P and T, they are anti-commute, not commute. So that's the difference. So here, just assume there's, maybe I should call it some P prime or something different to the convention of P. But this kind of parity at fundamental scale, I think it's proper because we must have certain parity symmetry in quantum gravity because x and 2 minus x is reparameterization. So essentially, nothing changed. In some sense, it must be local symmetry. You can never break. You can never break a local symmetry. So now, if we turn everything into the standard kind of convention, then you can find that this mass mixed matrix have a strange, interesting formula. And here, just some slides that argue that if you represent all the impression in terms of the impression of Majorana modes, you can see that they exactly have the same form. And that's also the argument all the G coupling for diagonal must be the same. But for off diagonal, their strengths also must be the same, but it can have some different phase pattern. I will discuss later. So now we just assume that G and G prime, they are independent here. It turns out that this mixing matrix actually are not dependent on the relative scale of G and G prime because this is kind of just some diagonal matrix, this G. So regardless how large this G is, we will have the same, this so-called golden ratio pattern, which is very close to the experimental measurement. But in this calculation, I assume this Dirac matrix is kind of, it's diagonal